All right, so we are doing 1.5 day 2, which is another day of parent functions and transformations. Notice the warm-up is write the equation of each parent function and graph it. So go ahead and pause your video and do that. You really need to practice to make sure you know what these look like. You get no points on a test if you don't know what something looks like, right? So pause your video, try them. I'm zoomed in because I already did it. Okay, I'm going to zoom out so that you can see what the first 4 look like. So check those. Your constant function, linear, quadratic, cubic. Notice in the quadratic function, the cubic function, I have those 3 points in each that you need to have accurate there. Here are the next 3. Squared function, once again, on square root, you can see the 3 points that you need. On reciprocal, you can see that you need the vertical and horizontal asymptote and that 1 point and -1 point. And then your absolute value, V-shaped with those 3 critical points. Okay, so what we are going to talk about first today is vertical and horizontal dilations. So when we're talking about vertical and horizontal dilations in Algebra 2 with trig and in integrated, we called them stretches and compressions. Or you would also say if it's getting wider or narrower, right? But in pre-calc, we're even more specific. We call them vertical compressions, vertical stretches, horizontal compressions, and horizontal stretches. So these are the words that you need to use. So these are the words we will use. Let me get this out of the way. I drew it there for a reason. Oh, took my S. Okay. These are the words we will use. Okay? So we are using vertical compression, vertical stretch, horizontal compression, horizontal stretch. We're not saying narrower, wider. We can talk about those out loud, but when we write down to describe what's happening, those are the 4 different types that you would write down. Okay, so let's talk about a vertical compression. So first off, we're going to use g of x once again, equals. You can tell that there is a vertical compression because there will be a coefficient in front of your parent function. Okay, same thing with a vertical stretch. There will be a coefficient in front of your parent function. Remember, f of x is the parent. So the difference is that if that a value is in between 0 and 1, usually people call it a fraction, but I don't like saying that because 3/2 is a fraction and it's not in between 0 and 1, or 6/3 is a fraction, but it's not in between 0 and 1. But if it is in between 0 and 1, that is going to be a vertical compression. So, for example, if you think about a number in front and it is, let's say, 1/2, that is going to be a vertical compression. What does a vertical compression look like? Okay, so think about vertically from the top and the bottom, compressing this absolute value function. What's going to happen to it? What's going to look like? It's going to get wider looking. Okay, so in other words, if we had, I'll use absolute value once again, absolute value right here, and that's the parent. When I vertically compress it, it is going to get wider, right? Okay, well, how do I know if it's a vertical stretch? If there's a coefficient in front of the parent and that number is greater than 1, and I should say the absolute value of that number because the negative wouldn't matter, then it's going to be narrower. Wow, can't spell. Narrower, right, or skinnier. So if this was the parent, okay, I'm just using absolute value because it's easy to show on this, and there was a number, a coefficient in front of your parent that was bigger than 1, that means that there's going to be a vertical stretch. So think about stretching it vertically this way and this way. It's going to get narrower. It's going to look like this. Okay. I don't want to imply this is going up and down. I'm just saying pulling from this point, pulling from these arrows. Okay? All right, next, horizontal compression. So horizontal compression is when you have g of x equals, or both horizontal and vertical and compression, or both g of x equals, and then there's a coefficient in front of x inside the parent function. So once again, a coefficient in front of x inside the parent. Okay? Now, let's talk about what it looks like first. So horizontal compression. So here's my absolute value function that we'll think of. If I'm pushing in this way, it's gonna get narrower looking. Okay, now we need to know what does that. That is going to be when that a value is greater than 1. Okay. All right, last but not least, this is obviously going to be wider, and this is when that a value is in between 1 and 0. So here's what the parent looks like. And there will be, this is a horizontal stretch. So I'm stretching it this way, and it would be wider. Okay, so let's make sure, that was a lot of information here, that we can see what's what. So I did parabolas down here, quadratics, instead of absolute values. Okay, so here's what the parent looks like. Once again, it's really important to be able to say it in words. So I'll do it in words before we actually even draw it. And then we'll prove with numbers that it actually is what it is. Okay, so this is the parent right here. Notice it's a number in front of the parent. Okay, it's a number in front of the parent if I circle the parent. So this is vertical. And then the number in front is a number bigger than 1, so it is a vertical stretch. Okay? All right, just to prove it, plug in 0, you get 0. Plug in 1, you get 2. So notice those points that were here and here are now up there. So what's happening is that the graph got narrower when it got vertically stretched. So no, you don't have to do points for accuracy, but they should be on the inside of where 1, 1 would be and where negative 1, 1 would be. Okay, so once again, here's your parent, numbers in front, so vertical. And then number in between 0 and 1, so this is a compression. So in the future, what I would say is vertical compression. I would picture in my head smashing it in between my hands. It got wider. And I would say, okay, it looks something like this, right? But just to prove to you that it did get wider, let's plug in values. Plug in 0, you get 0. Plug in 1, you get a half. Plug in negative 1, you get a half. So it does get wider. All right, next one. So if you look at this one here, the coefficient is on x inside of the parent. So if it's inside, in front, it's a horizontal. And then how I tell students to remember it is usually when the number is bigger, with vertical, it's a stretch. So this is compression instead. All right, when you plug in 0, you get 0. When you plug in 1, you get 4. Negative 1, you get 4. So if you look at a horizontally compressed, it's much narrower. Finally, inside the parent, so horizontal, in front. And the 1/2, usually with vertical, that would be a compression, but this is a horizontal stretch. It's the opposite of that. So plug in 0, you get 0. Plug in 1, you get a quarter. Plug in negative 1, you get a quarter, right? So you can see that this is stretched horizontally. Okay. So if we want to make sure we understand everything that we need to know, I honestly, and be very seriously, I memorize one. I memorize vertical stretches, and then everything else falls into place for me. So if I see a number in front of the parent that is bigger than 1, I know that's a vertical stretch. So that tells me if the number is smaller than 1, that's a vertical compression. Then I think, okay, what about horizontal? Horizontal would be inside, and if it's bigger than 1, it's not a stretch, it's a compression. And then if it's smaller than 1, it's not a compression, it's a stretch. Okay, last thing that we have to talk about before we start graphing is reflections. So when you were in integrated in Algebra 2, you did only vertical reflections. And that is when there's a negative in front of the parent. Okay, that is a mirror image over a horizontal line. So I'm going to use the square root function as my parent right here. Okay, so if I wanted to reflect that vertically, I would be reflecting it over a horizontal line, and it would look like that. It kind of looks like it moved down, which it didn't. So there we go. Okay. Now, a horizontal reflection, you'll have f of negative x. So inside the parent, there will be a negative in front of x. And this would be a mirror image over a vertical line. So, once again, we'll use the square root function. This is what a horizontal reflection would look like. Okay, so it's here once again, but just to make sure everyone can see what it looks like. This is the parent 001142. This is the parent. All right, so negative in front of the parent is a vertical reflection. Okay, so if you want to think about why that actually happens, if you plug in 0, you still get 0. When you plug in 1, you get -1. And when you plug in 4, you get -2. So you can see that that's what actually happens. It's a vertical reflection. Okay, this right here, there's a negative inside the parent in front of x, so that's a horizontal reflection. So, once again, think about what that looks like. If you plug in 0, you get 0. If I plug in 1, I get imaginary, so I can't do that. I have to plug in negatives. If I plug in -1, I get +1. If I plug in -4, I get +2. And that's why it looks like that. Okay. So now what we're going to do is we are going to graph multiple transformations being done. So this is exactly how it looks like on your test. It'll give you an equation. It'll ask you to identify the parent. It'll ask you to describe the transformations. It'll also tell you, and see here, graph f of x with a dashed curve. So you're graphing the parent with a dashed curve first. And then you're going to do a solid sketch of the new function. Okay, so first off, let's figure out what the parent is and then graph it. I can see this is x cubed, so this is the cubic function x cubed. So now I'm going to graph the parent. So remember, for the parent of x cubed, I need 0, 0, 1, 1, and -1, -1. And then very gently with a dashed curve, I'm going to graph that parent. See that? Okay, now we're going to state all the things that are happening on this graph. So we'll start, I'm going to move left to right just so I can see each one. So first off, there's a negative in front, okay? So notice that's outside the parent, because here's the parent right here. It's outside the parent in front, so that is vertical reflection. So I'm going to call this number 1 right here, and color coordinate and number. Vertical reflection. All right, next thing I notice is this 2 in front of the parent. So that's vertical once again. Now remember, a number bigger than 1 is going to be a vertical stretch. All right, next, I have this minus 1, right? So realize the negative is part of the function, or sorry, the parent, the general function, sorry, not the parent. So g of x equals a times x minus h squared plus k. And this one is a cubic function, so cubed, my bad. So the minus is there. So remember, when I see that, all that I'm doing is taking this number right here. And if it was a plus, that's like minus a negative number. So this means that it is moved right. So don't just put right. You are doing a horizontal translation. Right 1. So make sure you write down all of those words. Yes, there's abbreviation. You can abbreviate horizontal with this and translation with this, and then maybe put R1, but please don't just put right 1. All right, last one. I don't want to do blue. Let's do orange. Okay, this right here. Now, of course, that's going to move my graph down 3, but make sure you put first vertical. You can abbreviate vertical that way. Translation, you can abbreviate it that, down 3. All right, now I'm going to do all of these things. I'm going to perform this here. So I'm going to start with moving this point right here, how far it's moved right, left, up, and down. So it's moved right 1, down 3. So I'm going to move it right 1, down 3, and that's my new point. That was at 0, 0. Now I know that I have to vertically reflect it and vertically stretch it. Okay, so think about stretching, pulling on those arrows vertically, right? This is going to become narrower. So it's going to become narrower, so it's not going to go through these, it's going to come this way, right? But also it's reflected. So because it's reflected, it's actually going to go down this way, right? I don't want to hit this point right here because it's vertically stretched, it's narrower. Same thing here, like so. And that's what it looks like. Let me get my eraser out to erase that little point right there. Now, you might be looking at it and be like, I can't even tell that it's narrower. So if you're taking your test and you want to make sure that we know that it's narrower, you can always put like narrower here so we know off to the side. Okay? All right, so let's move on to the next one here. H of x equals the square root of 2 minus x plus 1. So once again, the general function for this, let me change this to blue, is h of x equals a times the absolute value of x minus h plus k. So notice, the first thing that you should notice is underneath the square root symbol, this is not written correctly. Okay, the x usually comes first. And actually, let me rewrite this here. I'm going to do b times x minus h plus k. Why? Because this can be a horizontal stretch or compression here, right? Okay, so let's reorder this. We have h of x equals square root of negative x plus 2 plus 1. All right, so the next thing you should notice is that this x right here has to be positive. So now I have to factor that negative out. So now I have the square root of negative x minus 2 plus 1. And this is what we're actually graphing right here. Parent function is the square root function. Let's go ahead and do a dashed curve of that. 0, 0, 1, 1, 4, 2. Okay, let's go through each part and see what's happening here. So we have this negative in front of x, but it's inside the parent. So that is horizontal. And since it's a negative, it's reflecting. So horizontal reflection. Next, we have this minus 2, so that's right 2. So I'm going to say a horizontal translation, right 2. Finally, I have this plus 1 on the end, and that is a vertical translation, up 1. Okay, so now I'm ready to graph this. I already have my parent graph. And now I'm going to look, remember, I'm going to use this 0, 0 as a guide and say, has it moved right, left, up, down? It is moved right 2, up 1. So move it right 2, up 1. So that's where the new 0, 0 is, the new critical point. There's also a horizontal reflection. Remember, horizontally opposed to vertically. This is vertical, so I'm not going that way. Horizontal reflection is going this way. And that's what my graph looks like. Things that we could ask you as a follow-up on your test here is like, what's the domain and range of your function? All right, so my domain would be negative infinity to 2 with a bracket, and then 1 to infinity with a bracket on the 1. All right, here's the last one. First thing I notice about this one, so we gave you ones that are more challenging together in class. The ones that you have to do in your homework are not as challenging. But I want you to realize that this function can be rewritten as 3 times 1 over x minus 2 minus 1. Okay? Because if I were to distribute the 3 to this inside this fraction, the 3 would go here, and I would multiply that by 1, and I would get this. Okay. So I'm going to keep that in mind as I'm doing this. You don't have to rewrite it. It just helps usually. Okay, parent is the reciprocal function, so I'm going to go ahead and graph a sketch of the parent here. Remember, I'm going to use dashed lines for the actual parent. I always use dashed lines for asymptotes, so that's not going to change. But when I go to draw the parent here, I'm just going to do very lightly dashed lines here. Dash curves, I should say. On your test, it says draw the parent every single time. Just make sure you're drawing that. That's a point. It's a free point. All right, let's describe the transformations. This is a 3 in front of my function, so that's vertical. And then the 3 is going to stretch it. This is a minus 2 right here, so that's going to move it right 2 because it's coming off of x. So I'm going to say horizontal translation right 2. And then last but not least, vertical translation down 1. All right, I'm ready to graph this, and this will be it. So I'm going to, my critical points for this, I'm going to use my asymptotes as my critical points. So I'm going to start by regraphing my new asymptotes. My new asymptotes are moved right 2. So the vertical one is going to be right 2. Like so, right? And then the horizontal one's going to move down 1. So right here, like so. Right? Not too bad. Now remember, there's usually a point right here and right here. Up 1 and over 1, down 1 and left 1 from the asymptotes. But there's a vertical stretch. So you have to stretch that point vertically from the horizontal axis. Stretch that point vertically from the horizontal axis. So instead, ooh, that was a little crooked. So instead of going through that point, which was once again right there, I'm going to be pulled away from it. Okay, and then I'm going to erase it because I don't need it. So this point that is right here, I'm going to say that I'm being pulled away from that. And there's my vertical stretch. Pulled away vertically. Okay, that's it for today. Go ahead and there's a worksheet for you to try a few on your own.